Okay, so I want to take some time to review with you regression, just a basic review. We'll look at the process of least squares and how that works. We'll take a quick look at the assumptions and potential problems when those assumptions are violated of regression. We'll look at a couple of measures of goodness of fit, and then talk about linearizing nonlinear models. Okay, so here we are. We have a set of x and y data points, and I wanted the whole point of this is I want to develop find the relationship between these two variables x and y with a model. Right? I wanted to find that relationship with a model, and the simplest model is a straight line relationship. So I want to find the line that best fits the data, right? Best fits that relationship. Okay? So I'm going to slap a line in here that minimizes the distance from the points. And it's a specific distance in least squares. If we assume that the x's are the independent variables, they don't vary, then it would be the y's that vary, and those are the ones that we want to, those distances are the ones that we want to minimize from this line that supposedly represents the relationship between x and y. And that line has an equation y equals a plus bx, right? Slope is b, y-intercept is a. And I want to minimize these distances, these red distances, the distance from the data to this model. And I don't even know where the model is yet, so that's what we're looking for. Right? And we're going to actually take these distances, square them, because I want to make sure that it's there are no negatives in here. I want to add up all of the distances. The easiest way is to square them. Add them all up and minimize that time, or that distance, right, from this line. And that's called, that sum of distances, squared distances, called the error sum of squares. It's the error that the line does not explain. Okay. So we're going to minimize that with an equation here. We're going to minimize the distance from the y values, the data, right, to the line. Y hat is the predicted value. If we have a particular line, that's the predicted y value. We want to minimize those, and recognizing that this is the y of the line, we know what the equation of the line is. We can substitute that in. yi and xi are just data, so those are knowns. Right? So the only unknowns really on this right-hand side of the equation are a and b. Okay? So if we take the first derivative with respect to a and set it equal to 0 of this function, we get one equation with two unknowns, a and b. If we take the first derivative with respect to b and set it equal to 0, we have a second equation with two unknowns. So with two equations and two unknowns, we can find the equation of the slope in terms of x's and y's, given data. And then plugging that back into the equations, we can find the equation for the y-intercept, which happens to be this. And that's it. That's pretty much least squares. You can expand that out to as many x's as you want, because then we would just have that many more equations, right? We would generate equations by taking the first derivative with respect to the coefficients of the x's. Right? So we can have as many x's as we want. If we have k x's, that's the number of x variables. I'm starting with 2 here because this first one is x to the 0 power, if you want to think about it that way. That's a standard way of looking at it. And we could easily find, as a linear equation, we could easily find the betas. So a measure that's of interest, it'll come into play a little bit later, but it's an important thing to keep in mind, is this degrees of freedom. Represents the number of values in the final calculation that are free to vary without changing the answer. and that happens to be equal to the number of observations minus the number of independent variables that we're including in the model, the number of parameters that we're estimating. And we'll come back to that at the end and use that number. Okay, so that's it for least squares. So a couple of really important assumptions, really just so you have them in your head when you're doing this stuff, so you appreciate that the answer that you get isn't necessarily the perfect one, right? So some things to keep in mind. First is there's an assumption of homoscedasticity, which is that the variance of the errors in your model are constant, or is constant, I guess, across all values. Right? And we'll talk about that in a minute. I'll explain it in a little more detail in a minute. This is most common in so-called cross-sectional data. So, maybe taken at the same time, maybe geographically distributed. Right? Errors are also not correlated. So the one error does not depend on some other error in the data. This is common in time series models, where you're looking at what you'll be looking at. You'll be looking at time series models all the time, and this is a pretty common problem among those kinds of models. Right. The next thing is when you're specifying the model, the choice of x's is important. So if two x's are linear combinations of one another, you don't want to include both. You'll include one or the other, because otherwise you'll compromise the quality of the statistics of the model. Okay. And finally, x's and errors are assumed to be independent. So in other words, if you don't include an x that you think is important to include, then it would be, but it's related some way, then it appears in the error term, and therefore is correlated with the model, and that's not a good thing, right? You don't want x's and errors to be correlated. So the assumption is that they're independent of one another. So the opposite, or the absence of homoscedasticity, is heteroscedasticity. As I said, it's common in cross-sectional data, so-called, and the problem is that the coefficients, the betas, are no longer good estimators of the slope of the line, if it's a line. And so we don't want that to happen. We want these things to be independent, or I'm sorry, constant, right? This is pretty easily detected, not so easy to fix, but there are methods for doing so. So an example of homoscedasticity, if you look at a plot of x and y, you can see that the variance, no matter where you are, the variance of the errors are, or is, constant, right? It's pretty tight all the way through. Here's an example of heteroscedasticity, where down here with small values of x and y, the variance of the errors is pretty small, but up here it's pretty large, or larger anyway. Statistically larger? I don't know. We'd have to do some statistical tests, right? And this is the name of one such test. There are many, many tests out there. So anyway, and here's a way of finding it out, and there are ways to fix it as well. Okay, now the problem, the assumption of the problem of autocorrelation. We don't want this to be happening, right? As I said, it occurs, or it's common. I won't say it occurs primarily. I'll say it's common in time series data. Again, if there is autocorrelation, the coefficients are not the best estimates of the slope again. And there is a way to detect this, and there are methods for fixing it. We will not look at either one. I'll just mention that there's a statistic called the Durbin-Watson statistic, should equal 2. So we can calculate that statistic from our data, and this value should be statistically equal to 2. And there are tables, standard tables of Durbin-Watson statistics that will, given some degree, the degrees of freedom that we have, will tell us, right, is this within, a certain confidence level of 2, of the value 2. That's the way to detect it. That would be an easy thing we could do if you chose to. Now, multicollinearity, that is the x's, 2 x's represent the same thing. Often this is a problem. Again, it affects the quality of the coefficients, the betas. We don't want it. It can be detected using the correlation matrix of the independent variables. And if the correlation is low, then it's probably okay. If they're high, then there's a potential problem, and anywhere in the middle is a judgment call. Okay. And then finally, the correlation between x's and error terms. If you leave an x out of the model that you think belongs in there, it causes all sorts of problems. So the best thing to do is, if you think that an x belongs in the model, you should include it. So that's a really quick and dirty review of some econometrics, a full year of econometrics in 10 minutes. Okay, so the next thing I want to look at is the goodness of fit. R square is a standard value. It goes from 0 to 1. And the idea is that it captures the proportion of variation explained by the model. So if this little point right here is a representative data point, and this is the line, the variance, or the total sum of squares variation from the average to all of the points, is this total sum of squares. The amount of error that's not explained by the line is here. This is the error sum of squares. We talked about that already, right? And then what's left over is the regression sum of squares. This is the amount of this that is explained by this line. Okay? So the R square is just the proportion of total variation that is explained by the line. And this is the equation for it. Now, if you plug in an extra independent variable, you'll invariably increase the R squared. So, but that's not real, that's a false increase, right? So we want to get a good, accurate view of the fit, and so we pay a penalty for introducing a new variable. And this is the adjustment. This is the value that you see in Excel under adjusted R square. Now, the standard error of the estimate is also called volatility for a model, and it's equal to this. It's just the standard error of the estimate. Bringing that up because we'll be using it later on. And this is an example of the pitfalls of using an R squared term. These two things from studies of like 50 different urban areas have an R square of 0.98. This is not causative, it's correlative, right? So these two things relate to another third variable that's not here, like, say, for example, urbanization, some urbanization variable. Okay, one last thing. We're running out of time here, but I want to just hit this without going into another video. Nonlinear models. So we want to be able to use regression, we have to linearize models. So they have to be separable, the so-called. That is, so that we need to be able to transform them to linear form. If we can't, then there are big problems. So, let's say, for example, we have a nonlinear x squared term. Well, this is an easy one, so we can just use substitution, right? So x squared is just a number, right? So let's create a new variable u and do the regression for this model, and a and b don't change. If we have let's say an exponential function, which you will have, these are typical growth functions. we can linearize this by taking the logarithm of both sides, and and then finding the the a's and b's from that after we've used substitution here. So this is u, z, d, whatever, right? And finally, this is another one we're going to actually look at this. This is a production function formula, and again, we can linearize this just by taking logarithms, right? And that's it.